Good morning. We are back in session for day 3 of the public hearing involving U.S. Airways Flight 1549. And I think we have received very good testimony and cooperation from all involved for the previous 2 days. And I know we will continue that into today. Mr. Benson, are you ready to proceed with the next panel?
Yes, sir. Our last topic is certification standards for bird ingestion into transport category airplane engines. And the board calls Marc Bouthillier, Robert Ganley, and Les McVey to the witness stand, please. And remain standing. Gentlemen, raise your right hands. Do you swear to tell or affirm the truth?
Yes.
Have a seat. And beginning with Mr. Bouthillier, could you give your full name and your job description, please?
My name is Marc Bouthillier. I'm an engineer, work for the FAA Engine and Propeller Directorate staff, which is part of the Aircraft Certification Service.
Good morning. My name is Robert Ganley. I'm the manager of the Engine Propeller Directorate Standards staff, also located in Burlington, Massachusetts, and part of aircraft certification.
Good morning. My name is Leslie McVey. I've been a flight safety investigator with CFM at GE for over 10 years. I'm also the principal engineer for environmental safety, and as such I track bird ingestions, amongst other things. Also in 2000 to 2002, I served on the Rulemaking committee, which developed the latest bird ingestion rules for large flocking birds.
Okay, our principal question will be Harry Reichel. Go ahead, Harry.
Good morning, gentlemen. I'm going to present the questions in 4 broad topics. I'd like to start off with the history of the bird ingestion certification requirements, and then continue and discuss the description of the FAA type certification process for turbine-powered engines. Then I'd like to go to specifically the CFM 56 compliance with the bird ingestion standards. And then to finish off, I'd like to discuss the development and the amendments to the engine bird ingestion standards, paragraph 3376 in the CFM. So I understand that you also have a presentation, and I'd like to, are you prepared for it right now to give the presentation?
The FAA is ready.
Okay.
Okay, I'm going to provide a very brief presentation to give an idea of the actions the FAA has taken to keep pace with this growing threat. I think, as we have heard in previous testimony, certainly the bird threat in the national aerospace system has been increasing. The goose population has been on the rise for the last 30 years and continues to rise. I think we heard some testimony from Dr. Dolbear stating that the large goose population, Canadian goose population, has increased 4-fold since the 1990s. In addition, aircraft flights have been increasing on the order of 2 to 3% per year. With this increase in population and flights, I think it's to be expected that our chances for large bird encounters would also increase. A little bit on the history of the rule. We added specific engine bird ingestion requirements in 1974 via Amendment 6 of our regulations. At this point, it addressed small, medium, and large birds up to 4 pounds. We've had 2 major revisions to our regulations since 1974, in the year 2000 and the year 2007. In 2000, we changed the bird sizes the bird quantities, the test conditions, and the pass-fail criteria. Later in 2007, we also introduced large flocking birds. The changes in 2000 and 2007 were driven based on the observed change in threat and service. The standards were also deemed necessary to ensure that we had a fleet-wide acceptable level of safety that met our safety objective. A little bit on our safety objective. All type certification rules have a basic intent or objective that is related to safety. Environmental threats for things like bird, icing, rain, and hail, the threat that we're trying to address and to ensure is continued safe flight and landing. Specifically for bird ingestion, the threat that we've seen in service have been multi-engine power loss. As a result, our safety objective is to ensure that we don't have any significant accidents due to multi-engine power loss due to flocking birds, to ensure that they do not occur at a rate greater than 1 in a billion airplane flight hours. This rate is sometimes referred to as extremely improbable. It's a very conservative aviation industry accepted safety standard. It reflects the FAA's view of long-term acceptable risk, and it is also consistent on how we handle many critical aircraft systems, such as flight controls. In light of that, certainly this event is telling us something that I think we need to take a look at. The FAA has already, the Engine and Propeller Directorate, made contact and initiated activity with both industry and EASA to update our bird ingestion rule database through 2008 to better reflect the current threat and service. Of note is that our last update was in 2000. Our 2000 database was the basis for our current rule. Our current rule is very data-driven. It includes data that covers a 30-year time period. This 30-year time period includes in excess of 325 million civil turbine engine flights worldwide, and includes over 8,100 specific bird ingestion events. Basically, once we update this database, there'll be a reevaluation of our rule effectiveness and determine whether or not it still meets our overall safety objective. Depending on the outcome of that determination, that will drive any future action. That action may include rule updates, policy or guidance updates. At this point, just to mention that, our national airspace system safety is high, but events do occur. The purpose of this slide is to show that no single element of threat management can address the concern alone. This pie chart depicts aircraft certification. Our bird updates in 2000 and 2007 are intended to address that piece of the pie. I believe that, we heard a lot of testimony early on about airport bird control and wildlife mitigation. We heard a lot about bird radar research, enhanced visibility, avoidance. That's another piece of the puzzle here. Also, awareness, vigilance, air traffic control, flight operations. What do you do if you encounter birds? And lastly, some of the off-airport wildlife and management at the state and local level as well. So I think all of these organizations contribute to the overall mitigation of the bird threat. In conclusion, it's not reasonable to assume that we can design an engine that can withstand birds of any size under any condition. I mean, there are some technological and design limitations within an engine. So really, what's really needed is a high-level systems management approach to address this issue. I just kind of put things in perspective a little bit. You know, we've heard from prior testimony that, you know, one engine ingested 2 large 8-pound birds for a total bird mass of 16 pounds. Another engine ingested at least 1 large bird, so 8, perhaps 16 pounds of birds. When the 5B engine was certified, at that time, the test was conducted with a 4-pound bird. If that test were conducted today under our current certification standards, it would be tested to a 6-pound bird. So this event far exceeded any of our current certification requirements. The performance of the engine exceeded our certification requirements for the ingestion of a large bird. The requirements for the ingestion of a large bird are a safe shutdown. A safe shutdown is identified as things as no uncontrollable fires, no release of hazardous material through the engine casings, you know, things like that. Certainly, the engines on US Air Flight 1549 exhibited safe shutdown. One engine safely shut down. In fact, one of the engines continued to operate at a power level that allowed the engine to still generate electrical and hydraulic power, which partially contributed to the successful forced water landing of the airplane. And kind of the takeaway from that is, even though a test might be run to a 4-pound bird standard, it doesn't mean that if it ingests a 4.1-pound bird that it would not be able to withstand that. I think that does point to the inherent conservatisms that are built into the engine designs in relation to the certification standards. That concludes the FAA presentation, and we're ready for any questions.
Thank you, Mr. Ganley. My next questions are directed to the FAA, either witness. And I'd like to talk about the airworthiness standards for aircraft engines, paragraph 76. And I'd like to ask you to please provide a brief history of the rules of foreign object ingestion from the time they were introduced in 1974 to the present, and to also please highlight the significant technical changes that each amendment introduced.
Yes, you're correct. The engine certification requirements are located in Part 33. The current bird standard is under Section 3376. The bird standards were originally introduced into Part 33 in 1974. That was under Amendment 6. Those new standards had 3 elements to them: small and medium flocking birds and large single bird. The flocking bird requirements represent the multi-engine ingestion scenario, somewhat, well, the same as US Air here. And the single large bird test represents a severe single-engine event. The bird sizes at that time were 3 ounces for small birds, 1.5 pounds for the medium flocking bird, and 4 pounds for the large single bird. The flocking bird standards do require run-on. The run-on for these original standards was 5 minutes with no throttle movements, with a thrust loss no greater than 25%. And these tests were run at a rated takeoff power and at critical target locations. The number of birds that are required for the flocking tests are a function of the engine size. Larger engines are required to ingest a greater number of birds. But the number of birds that are required, they're targeted on critical features on the front of the engine to exercise those, in a conservative manner. The large single bird standard does not require run-on. That's a safe shutdown requirement. I think Bob had hit on that. The requirement there is that there would be no uncontained failure, no fan blade failure that would result in radial expulsion of debris through the engine casings, no fires, no compromising of flammable fluid carrying components. Mount integrity will be maintained, so the engine stays with the aircraft. And if the engine does continue to operate, the engine does need to be able to be controlled, at least to a safe shutdown. So those were the original standards. Since that introduction, those standards have two significant revisions, and as Bob had mentioned, in year 2000 and 2007. That was Amendments 20 and 24. The Amendment 20 standard was a significant revision to the original standards. There were some significant changes to the bird sizes and numbers as a function of engine size, the run-on requirements, pass-fail criteria, and some items related to how the tests are actually conducted. The main features of the Amendment 20 change in 2000 was change to the medium bird size, where originally it was 1.5 pounds for the larger engines. That was changed now to a mix of 1.5 and 2.5 pound birds as a function of engine size, where the bigger engines get bigger birds and or more of them. Another significant change was to the large single bird size, which originally was 4 pounds for all engines. That was changed to 4, 6, or 8 pounds, again as a function of engine size, where the larger engine gets the larger bird. Third major change was to the run-on requirements for the flocking bird tests. Originally they were 5 minutes run-on with a locked throttle, no throttle movements. That was revised to a 20-minute run-on requirement with throttle manipulations. The throttle movements are in the form of a profile that would simulate an air turnback scenario. For example, if you had a multi-engine bird ingestion during takeoff and there was a need to return to the airport, this 20-minute demonstration would show the ability of the engines to be handled. You modulate thrust so you can safely fly the airplane back to the airfield. And these changes were, the Amendment 20 changes were the result of bird threat studies that have been conducted in the late 80s to the later 90s, indicating a worsening threat and the need for some more stringent requirements to maintain safe operations into the future. These 2000 standards were further revised in 2007. The main feature of this change was the inclusion of a new test requirement for a new bird threat class. This is the threat class we call large flocking birds, and we define that as birds greater than 2.5 pounds. This is a flocking bird requirement, also requires run-on. The bird sizes for this particular test are either 4, 4.5, or 5.5 pounds as a function of the engine size, where the bigger engine gets the bigger bird. Bird quantity is 1 in this case, where with the small medium flocking birds it was variable, but it's 1 in this case. The run-on requirement is the same 20-minute air turn back scenario with throttle movements showing that the engine can be handled so that the aircraft can be flown safely back to the airport. And a little bit different than the medium test where the maximum thrust loss is 25%. For this large flocking bird test, the maximum thrust loss allowed is 50%. And the standard was also the result of the continuation of the bird studies I had mentioned from the 80s right up to 2000, indicating an increasing threat, worsening threat, in service, and the need for more stringent requirements to maintain safe operations into the future, especially for this new threat class, the large flocking birds of those greater than 2.5. Now these standards were also, the rulemakings were also joint efforts with the European Authority, EASA, or JA at the time. They were joint efforts, and our current requirements in Part 3376 are identical to the EASA standards and their certification specifications. I think it's CSE 800, so they are identical. So just a real quick summary, original standards, bird ingestion standards into the engine cert code in 1974. 2 significant revisions since then in year 2000, 2007. Those changes are a result of bird threat studies showing a worsening situation and the need for more stringent requirements. And we went forward and modified or revised the rules to try and keep pace.
Thank you. One of the questions I had with respect to was with respect to triggering these amendments, the one in 2000 and 2007. What was was there an event that triggered them, or is there someone who analyzes the data and is the data analysis triggering it? What causes an amendment to be started?
Well, in general, for the bird rule, or for, I guess, probably all the rules, if if it becomes evident to us that the safety objective of the rule is not being met, then we would certainly institute some sort of a formal program to understand that situation and potentially go and revise our rules or revise our methods of compliance, what have you. Specific to birds, again, if our safety objective is not being met, or if it becomes evident to us that the bird ingestion rates are higher than our rule assumed, or if any products are not performing in accordance with our expectations for some reason, those would be reasons to go and conduct a study to understand what that situation is and develop a plan to get back on track. Back in history of the driver for these other changes, again, there were a large number of bird threat studies that started in the 70s into the 80s, and those studies, I believe, were on and off a little bit. But these were the result. These changes were the results of threat studies, primarily in the later 80s, through the later 90s.
Thank you. If the bird ingestion certification regulation were amended today, what engines would be affected by this change? Specifically, would the CFM 56-5 be affected, or would only future engines be affected?
Only new engines would be affected by the rule updates. Basically, what occurs is that you have an effective date to a new rule. Any application that comes in after that effective date needs to comply with the current standards.
Thank you. I'd like to address the next few questions to the FAA, and this is a description of the type certification process for turbine-powered engines. Would you please briefly describe the overall process that a manufacturer must follow to obtain type certification for a turbine engine?
The overall type certification process is outlined in Part 21 of our regulations, and more specifically in FAA Order 8110.4. At a very, very high level, the process begins when an applicant submits an application. Following the receipt of an application, we typically hold a preliminary type board meeting with the applicant. It's at that point we begin to discuss the overall certification basis and other specific project details. Following that, typically a detailed compliance checklist and compliance plan is put together that describes in more detail the specific methods of compliance to each of the regulations. Following that, typically test plans are submitted, analysis plans are submitted, they are approved. The applicants go off and actually execute the tests. Upon completion of the tests, the results of the tests and/or analysis are documented in certification reports. The certification reports are approved. Upon approval of all the pertinent reports and demonstrating compliance to all the applicable regulations, a type certificate is granted. At a very high level, that's our type cert process.
Thank you. And could you please briefly describe the kind of bird ingestion tests that are conducted on aircraft turbine engines to satisfy 3376, and what the pass-fail criteria generally are for each type of test?
Yes, again, 3376 is does contain our bird ingestion standards for engines. 3376 is also a test requirement. Okay, it's not an analysis requirement. It is a test requirement, so there'll be a series of certification demonstrations that the manufacturer would have to, conduct. For large transport category engines, the program generally has three elements. That would be a medium flacking bird test, a large flacking bird test, and a large single bird test. The medium flacking bird test is a full engine test. It would require ingestion of a varying number of 1.5 and 2.5 pound birds as a function of engine size. The ingestion occurs at a series of critical conditions, rated takeoff power. The number of birds that are required to be ingested will be targeted at critical locations on the front face of the engine. Bird speed is also optimized to get the maximum slice mass, into the fan blades for a fan engine. So critical bird speed is used too. So there's a series of very conservative parameters that go into the test. The pass-fail criteria for this test is the ability to conduct, as I mentioned, a 20-minute run-on profile. For the medium test, the maximum thrust loss allowed is 25%. But the engine has to complete its 20-minute run-on profile with throttle manipulations representing an air turn back. That profile includes a period hands-off after the event, and then a sequential reduction in power to approach, and then a burst to go-around power, and then finally coming back down and shutting it down. So it's a very conservative test from our perspective. The large flocking bird test really is similar, although the bird size and numbers are different. Again, this will be a full engine test that will be conducted. Bird quantity is 1. Size of the bird is anywhere from 4, 4.5, or 5.5 pounds as a function of engine size. This test is also conducted at high power, and there is a 20-minute run-on requirement also with throttle movements to simulate the air turn back situation. However, the maximum thrust loss allowed for the large flocking bird test, as I mentioned, is 50%. It's 25% for the medium flocking test, but for the large flocking test, it's 50%. So that would be the second major test. Third would be a large single bird test. This can be a full engine or it can be a rig. There are a couple of different methods of compliance that an applicant can choose. Bird sizes here are either 4, 6, or 8 pounds as a function of engine size. A larger engine gets the larger bird. No run-on required for these large single birds. These are safe shutdown requirements. Again, those requirements are that there'll be no uncontained failures, no radial expulsion of high-energy debris through the casings that could impact the airplane or its systems. No fires, no compromising of flammable fluid-carrying components, mount integrity. The engine needs to remain with the aircraft. And again, if the engine does continue to operate, it must be controllable, to a safe shutdown. And again, the ability to run on is not required. If you also do look at the 3376 standard, you'd also find a small flocking bird test in there. There are small flocking bird requirements for all engines, from the smallest to the largest. However, we typically don't do small flocking bird tests for the transport category engines. There is a clause or a exclusionary element to the rule that allows a large flocking bird, a small flocking bird test to be eliminated under certain conditions, and those conditions are related to inlet design. If the inlet is designed such that a medium bird can pass through unimpeded and impact the first rotating fan stage, then the small flocking bird test is not required. Rationale there is that the medium bird can pass unimpeded, that it's a much more significant demonstration of ingestion capability than the small flocking bird test would be. And the rationale, well, that's one of the rationale. Small birds tend not to cause, a lot of damage. And also the small flocking birds historically have not been a significant player in power losses. Conversely, if the inlet is designed with other inlet structure like inlet guide vanes, or if the engine is small enough where a medium bird may not pass through unimpeded, then a flocking bird test would be conducted. But for our typical large transport category engines that we're talking about today, they tend not to have inlet structures like that, so the small flocking bird tests are generally not required. And that's a summary of the type of testing that these engines would normally undergo.
Thank you. This is a question specifically of this particular engine, and if you would please describe the joint certification process that is with the FAA and the EASA cooperation that is unique to the CFM engine products, and how differences in the regulations between FAA and EASA are addressed.
Yes, the CFM engine program has a unique arrangement that's been in place since the early 70s. It's unlike really any other certification validation type process that we have in place. I think a testimony yesterday that Mr. Bresnahan described the typical validation process. In this process, the procedures are documented in a management plan. At the time of the certification of the 5B, the management plan was between the FAA and the DGAC of France. Obviously, today it's between the FAA and the EASA. This management plan is actually even outlined in the implementation procedures for airworthiness that are called out in our bilateral agreement. Basically, it's a parallel process. I think Mr. Hooper mentioned that yesterday. What that means is that both authorities are basically jointly certifying the engine together. It's not a serial process where the French is the state of design, certify it, and the FAA validates it. It's done concurrently. All meetings are held jointly between both authorities. CFMI is the type certificate holder, basically demonstrates compliance to both regulations and all of their certification test plans, reports. The authorities jointly approve all test plans, all reports, and when both authorities are satisfied that the documents meet the requirements of each country, FAR 33 on our side, JARI back in the the days of JA, and CSE requirements today, then we both issue our type certificates simultaneously. So at a very high level, that's the way the process works. Again, it's a parallel process that we get to the point at the same time rather than a serial process where the FAA may follow a foreign authority.
Thank you. Are there any differences between the current FAA standards and the current standards of EASA's CSE for bird ingestion?
The current standards for the FAA in 3376 Amendment 24 are identical to the CSE 800. I think it might be Amendment 1. That's today. So the current requirements are identical.
Okay.
And the rulemakings, they were concurrent. They were cooperative efforts between ourselves and EASA, J at the time.
Great, thank you. I'd like to talk about advisory circulars, and specifically AC 33-2B, which contains the FAA guides material for engine type certification. The guidance allows foreign object protection devices, such as screens or S-shaped ducts, to be incorporated into engines. Has any turbine engine manufacturer ever applied to incorporate any fan protective devices for certification?
You're correct that the rule does have a provision for inlet protection devices. That was included, a provision of that type was included in the original standards also when that was carried forward. However, as far as fan engines go, I have no experience with an applicant including a fan and inlet protection device as part of their engine type design or their overall program. It is allowed. There are provisions in the rules, and there is a statement in the advisory circular about that. But I'm not familiar with any fan engine inlet protection devices. If we looked at, say, rotorcraft, sometimes they will have like plenum type inlets that are not direct line of sight, and they have filters and things for dust and gravel and what have you. But as far as the fan engines, relative to your question, I'm not aware of any inlet protection devices that we've ever evaluated under the rule. Having said that, we have gotten suggestions in recent times about inlet protection devices. Folks have been recommending screens in front of engines, screen devices, mesh devices to be placed in front of an engine inlet. Again, we've never had any manufacturer, engine or airplane, propose to do that I know of. we at the FAA, we have concerns with that type of a structure or that type of a device. We do think that there are some serious technical challenges to that could result potentially in a lesser level of safety overall than a greater one. Some of the problem areas with screens, if that's part of your question, problems with operability and vibratory stresses on airfoils. A screen upstream of the engine will have turbulent flow downstream of it, and there will be inlet pressure distortion patterns that will be passed through the engine. Engines can be very sensitive to that, more prone to surge, stall, flame out. Same for vibe stresses on airfoils. These inlet distortion pressure patterns that will get passed through can drive airfoils closer to resonance or to resonance, so there potentially could be a greater chance of high cycle fatigue failures with those type of devices. We do conduct surge and stall testing and vibe stress testing for certification, and some manufacturers actually have used screens to introduce a certain level of distortion, to better test the engines under those circumstances. So we think that would be a challenge. Icing conditions would be another one. With screens, a mesh screen in front of an engine, and we, flight and icing conditions is common, and we believe that type of a structure would probably be probably a crew ice, readily. Any bridging of the meshes with icing in an icing environment, could result in airflow reduction or, again, inlet distortion issues. And any structures that do accrue ice, eventually will shed it. And any significant amount of ice on an inlet screen like that, when it is shed, most likely it would be passed through the engine, and the potential is there for some significant damage. And enough engine can, put the fire on the combustor too. So those are some significant areas. Failure of a screen. A screen mounted in the front of the engine would have to be a very heavy structure, very strong, to withstand any anticipated or any possible impacts. But mechanical systems, do fail at times. And if a large structure such as this failed in front of a large turbine engine, the potential exists for some significant damage and an uncontained failure. And that's a concern. And even if the device did not fail directly into the engine, if it went off to the side, then the potential exists for impacting airplane structure, wings, horizontal stabilizer, vertical stabilizer, control surfaces with a large structure like that. So that is a concern for us. Another potential problem area with screens, like in front again, will be a reduction in airflow at, say, windmilling conditions. And that would reduce the rotor speeds in the engine during windmilling. And if there's a need to restart, that's a more serious place to start from if your rotor speeds are down, and may even be more sensitive to the core lock issue. So inlet protective devices they're accommodated in the rules. I'm not aware on a fan engine one has ever been proposed. As far as specific to screens go, we think there are some significant technical challenges to overcome to do that, but the potential exists for maybe a lesser level of safety than a greater one, given some of the things I talked about.
Thank you. I'd like to address my next questions to the CFM witness, Mr. McVey. I wonder if you could, my first question is if you could give a brief description of the engine and highlight the damages to those parts that were germane to the event. Now, I understand that you have a presentation as well.
I do.
Yeah, would you like to give that one now?
Yes, please.
Yep.
This is just a short presentation, and a lot of it has been covered already by Mr. Bouthillier and Mr. Ganley. It summarizes bird ingestions and the requirements for certification on the CFM 56-5 engines, and covers briefly what we found in the accident engines. All larger engines have to demonstrate compliance with medium-large bird ingestion regulations. The number and weight of birds, as was said, depends on the size of the engine, because the larger the engine, the more likely it is to ingest a heavier and a higher number of birds. At the size of the CFM 56-5, when it was certified in the early 90s, it was required to ingest 7 1.5-pound birds at takeoff power, without losing more than 25% thrust, or require shutdown within 5 minutes, or even result in a hazardous condition to the aircraft. So to demonstrate success, you had to produce at least 75% thrust for at least 5 minutes after the ingestion. The large bird test required a 4-pound bird ingestion without hazardous consequences such as fire, uncontained fragments, or losing the ability to shut down. However, there's no requirement, as was stated, for continued thrust production. It's a safe shutdown test. In the late 80s, there was a joint industry agency working group meeting, and they were studying the need to increase the median bird requirement. This was, as mentioned by Mr. Bouthillier, this resulted in the Amendment 20 to the regulations. The CFM and DGAC of France at that time agreed that the CFM 56-5 should certify to a special condition in anticipation of these new regulations. And they would require 2.5-pound birds aimed at the fan outer panel and also at the core. The maximum thrust loss of 25% was unchanged. However, the run-on requirement was increased to 20 minutes, including throttle excursions to show operability. This was a significantly more stringent test requirement. The CFM 56-5B and 5B/B demonstrated full compliance with all these bird ingestion cert requirements, including the special condition. When we performed bird ingestion testing, as was mentioned, the median bird test, you fire the birds in across the fan face. The birds are aimed at least one at the core, the rest of them at critical locations across the fan blades. The test does use dead birds, by the way. The birds are fired in a volley, which must be within 1 second, and that's to simulate a flock encounter. The engine's at max takeoff fan speed, and the birds are fired at critical speeds, and this maximizes the fan blade stress condition. It's a deliberately stringent test, and it's designed to simulate the worst encounter that you could get in service. When we ingest birds in service, it's typically much less severe than the certification test. All birds will strike the fan blades on the way into the engine, but the vast majority pass through the bypass duct, which is, as you can see, that arrow bird through bypass. It's the large area out there. 90% of the air goes out there, and most of the birds go out there too. Even those that strike the spinner in the center will hit it, and they'll be deflected out through the bypass mainly. Some parts might go through the core. The pink region on the diagram shows the narrow annulus that a bird must be in to possibly enter the core. This is just a small percentage of the inlet frontal area, and even then, the bird will probably strike the fan blades and parts will be centrifuged out into the bypass again. Also, when you ingest birds in service, typically it's not at max takeoff power, which we did in the certification test. In fact, more than 50% of ingestions are on approach at more idle powers. So ingesting birds at max takeoff power into the core is unusual. And I'd like to clarify one typical misconception that's often stated is that, birds aren't sucked into engines unless the engine's taxiing or standing still. That's when we'll suck birds into engines. But once the aircraft's moving down the runway at more than 50 miles an hour, whatever's in the way of that engine will get ingested. But it's only when it's in a direct line. That's why that pink area. If a bird's not in that pink area, it will not enter the core. For all these reasons, it's highly unusual to get a significant amount of bird into the core at takeoff power, and it's even more remote to get it into two engines in the same flight. However, in this event, that's what we seem to have had. When we looked at the FDR data, and I won't belabor this, it was covered the other day by Mr. Benson, we saw the ingestion event as the aircraft climbed through about 2,800 feet, doing 220 knots. The thrust decreased simultaneously on both engines. The number one engine, the left engine, the core speed still stayed relatively high, so it was providing electrical and hydraulic power. However, the fan speed was low, meaning that little thrust was available. The number two engine rolled back to sub-idle and was safely shut down. The result was insufficient thrust available to maintain flight, and the emergency landing was necessary. When we dismantled the engines, we found bird remains throughout the core and bypass flow paths of both engines. These were sent to the team at the Museum of Natural History at the Smithsonian and identified as Canada geese. a bird which averages around 8 pounds. And as has been stated, this is significantly heavier than the large bird requirement for these engines. And that's for the safe shutdown requirement. They're more than 3 times the weight of the medium bird requirement, which is continued thrust. From the booster inlet damage, it was clear there was ingestion into the booster and the core of both engines. The evidence indicates that only part of the bird entered the booster. However, based on the damage that we observed, the mass of the bird that entered was heavier than we saw during certification testing. We found consequent significant mechanical damage throughout the core, and that caused the loss of thrust on both engines. Notwithstanding these findings, the engines did react safely as required for large bird ingestion. One was safely shut down, and the other continued to operate. And that concludes my prepared material.
Thank you. I'm wondering if you could please give a description of the actual bird test conducted specifically on the CFM 56 5B and summarize the test results.
There was a series of tests performed on the both the 5A, the 5B, and the 5B/P. We performed component tests where we fired 2.5 pound birds at the spinner, the fan blades, and the booster IGV. For the fan blades and the booster IGV, we then took those components, installed them in engines, and performed run-on tests to show that they met thrust requirements and also durability requirements of the rules. We did the test I described, the medium bird test, 7 1.5 pound birds, 2 of them aimed at the core. We performed that run-on. In that test, we lost less than 5% thrust, which was well within the 25% thrust limit. We did an engineering test early on in the program with 2.5 pound birds aimed at the core and at the fan outer panel. In that test, we lost less than 10%, again, well within the 25% thrust limit. After the medium bird test with 1.5 pound birds, when we assessed the damage, that only did a 5-minute run-on, but the damage was not severe, and we believe it would have run on significantly longer, at much more than 75% thrust. When we certified the 5B/P again, we did component testing, firing 1.5 pound and 2.5 pound birds. The 5B/P was a derivative of the 5B model, and that's the engine installed on this aircraft, the 5B/P. We put aerodynamic and durability improvements through the core, and we tested 2.5 pound birds and 1.5 pound birds on the booster IGV, the modified IGV, and also performed a medium bird test where we fired medium birds into the core. In that test, we used the damaged fan blades from the previous 5B medium bird test because we hadn't changed the fan at all. After the volley of birds into the core, there was no change in thrust. So again, we met the thrust loss requirement, and we performed the 20-minute run-on as required. That's about it. These tests were accepted by the DGAC and the FAA, showing full compliance with the regulations.
Thank you. How large is the worldwide fleet of the CFM 56 engine?
We have something like 15,600 engines actually flying on commercial airplanes. There's another 2,500 on military aircraft. And we produced about 20,000 engines altogether. So total CFM time is over 120 million hours, and we've done nearly 500 million actual engine flight hours. The CFM 56-5 is about 25% of these numbers.
Thank you. I'd like to talk about the some engineering solutions, and my question may be difficult, but I'll address it anyway. Are there any other reasonable engineering solutions that could be incorporated into engine designs that may have prevented the Hudson River accident?
You've got to look at the turbofan, the way it's developed over the past 30 to 40 years. It's matured to a fairly similar design across the industry. It's a very balanced design. It's proven to be very safe, very reliable, and very efficient. When I say it's a balanced design, it has to meet a lot of different requirements from the regulatory agencies, from aircraft manufacturers, and for our own design practices. Part of these is you have to show airworthiness, there's safety requirements, there's noise, emissions requirements. You have to produce high thrust with high reliability and high efficiency. Just to try and improve single components for specific requirements, such as a very large bird, we could upset this balance and change the whole balance of the engine. And in doing so, you might not meet many of the other requirements, such as icing, operability, and things like that. So, to answer your question, no, I really don't see any reasonable engineering solution that can be applied to these engines at the moment. You have to remember that the heaviest bird we have to ingest into the core is a 2.5 pound. And in this event, we ingested 8-pound birds, which is more than 3 times that requirement. So this wouldn't be just a simple incremental improvement. This would be a major change in technology, a step change to do that.
Thank you. As mentioned previously, Advisory Circular 33-2B allows for fan protective devices to be incorporated into engine design. Could you please comment on this particular design feature on large turbofan engines? And also, as a follow-up, has CFM ever tried to certify a fan protective device?
Really, to follow up on Mr. Bouthillier's comments, no, we've never tried to certify anything like that. And we've studied the options. If there was something possible out there, we'd probably try and design it. We've looked at screens. My colleagues at SMECMA went away and diligently tried to calculate one, how you would design a screen. You've got to remember, the engine or the aircraft is moving at 250, 300 miles an hour, say. And if you've got a screen on the front, it's going to ingest an 8-pound goose. There's a lot of energy to be dissipated. And it couldn't be handled by a simple mesh or chicken wire or anything like that. We're talking, half-inch titanium rods in a 4x4 mesh. It would be a huge structure to try and withstand that impact. And as Mr. Bouthillier mentioned, the consequent other things that would happen, distortion of the airflow on the inlet, icing, you get pounds and pounds of ice building on that thing, and you would end up shedding ice into the engine constantly in icing weather. The consequence of screen failure, where you're going to impact the screen with a bird, you'll still end up with the bird and pieces of metal now going into the engine, which is going to be worse than the bird itself. And then other possibilities such as poor in-flight restart performance. In this event, they did do the in-flight restart on the way down, and that could have been affected. The engine, number one, did restart. It spooled down and fired back up. Again, that might not have happened with something like a screen on the front blocking the flow. So the detrimental effects totally outweigh any positives as far as I'm concerned.
Thank you. This next one is going to be a long question, so if you bear with me. We know that the event engines did not flame out at any time during this particular event. And from the review of the internal damage to the two engines during the teardown, I think we agree it is unlikely that any start attempt would have been successful in having the engine produce any further thrust. However, the crew was unaware of this fact, and they followed the checklist for a dual engine failure. And they still attempted to restart the engines, and now subsequently we understand that once we reviewed the engine, we found it was not possible to start them. And while it is unreasonable to have the crew diagnose engine problems during emergency situations, are there enough sensors within the engine? And can the engine digital controller be used to recognize such a situation so that it can alert the crew to forego any further start attempts and thus reduce their workload and save time for other priorities?
I think we'd have to study that very carefully. The sensors in the engine are there for controlling the engine, and modern FADEC, full authority, digital electronic controls have a lot of power. If you look at some of our recent engines, we can do stall detection logic, where you can detect a stall, and you can pulse the fuel flow to clear a stall. So there's capabilities there that can be studied for an auto restart, which might relieve the crew workload. I think in this case, the crew did see that the number one engine was operating with a relatively high core speed and a low fan speed, which could indicate that the engine was a stall and that the restart procedure might clear it. In this case, it wasn't that, because the engine core was damaged sufficiently that the airflow was just very low in the core, and it just couldn't run the fan. So I don't think it was a waste of time attempting that restart for this crew, but we'd just have to go and look at what can be done in the engine and what sensors we have and what the possibilities are. I don't want to take authority away from the crew. If it's a safety issue, if the crew can possibly get more thrust out of that engine, you've got to give it to them. And to have a control say, no thank you, we're not going to let you. You don't want to do that.
Thank you. My next questions are addressed to the FAA again, and these questions are concerning the development and amendments to the bird ingestion standards. I wonder if you could please explain the overall process used to develop new bird ingestion rules for the 33-76 paragraph rules.
Again, at a very high level, our process for rulemaking is covered by Part 11 of our regulations. More specifically, we have a rulemaking manual, an FAA rulemaking manual that's managed by our Office of Rulemaking within Aviation Safety, the AVS organization. Basically, the first step of our rule process is determine the need for rulemaking. I think as Marc had indicated earlier, this need could be based on, adverse field service experience. It might be an accident such as we're discussing today, safety analysis, items like that actually determine the need for rulemaking. Once it's determined that rulemaking is needed, our formal process takes over within the FAA, where we obtain approval to move forward. The first part of that process, it is the process that was used specifically on these bird regulations, is for the FAA to formally task an ARAC committee to go off and, evaluate, make recommendations. These recommendations would involve, recommendations related to changes to the rules and/or the policy and guidance that goes along with those rules. Usually the first step is to go off and put some work groups together, specifically for the bird rules. These work groups included representatives from, domestic and foreign engine manufacturers, the G's and the Pratts of the world, as well as foreign engine manufacturers, airplane manufacturers, Boeing in this case, foreign airworthiness authorities, JA at the time, EASA today, Transport Canada, as well as alphabet groups. My understanding is ALPA was also involved in this committee. The team goes off, they make recommendations to the FAA. The FAA receives those recommendations. In this particular case, the recommendations on our bird rules, because the FAA was so actively involved, as well as JA, in the generation of these recommendations, they were accepted fully by the FAA. And at that point, the internal FAA process takes over, where we go through the internal FAA comment process, the public comment process, the final issuance of the rule. And at each step of the way, any comments that are received are formally dispositioned, and if need be, the rule changed. But going back to this specific rule, the rule was adopted as received by the ARAC recommendation.
Thank you. I'd like to talk a little bit about the database itself right now, how you actually gather the data, and also how it's used. So and that's my question exactly. What data is collected? Who collects the data to support the rulemaking projects, and then how is it used?
I can answer that. Our current requirements do have a database supporting them. It's an extensive database. So our rules are data-driven. The data was collected and analyzed by the FAA ARAC rulemaking team, and I think Bob had mentioned some of this previously, but our data does cover a 30-year period through January of 2000. During that period, that does reflect about 325 million turbine aircraft operations, and the actual number of bird ingestion events in the database is a little over 8,100. That data also covers a full spectrum of civil operations, 2, 3, and 4 engine airplanes, all the major Western engine manufacturers, Western aircraft manufacturers, all their customers worldwide, and all the airports that those customers fly into and out of. The event data that was collected for each of these 8,100 events, we tried to be as complete as we could. Date and location, airplane information, the engine model information, numbers of birds that were ingested, the species. That's difficult to come by sometimes, so that's not 100% on that. But the results of the event, power losses, the effect on the flight, if there was any. So for each of these events, we tried to be as complete as we could. There are a lot of fields that we needed to fill in. Now, the way that we did it was to work back through the manufacturer's field representatives to the operators, the folks who actually fly the airplanes and have the events. The manufacturers have field reps assigned, to their customers permanently, and those folks work closely on a variety of issues, economic issues, safety issues, a variety of issues, and there's we believe, a good working relationship, and we thought was a great way to go back and get the data directly from the operators. So we feel that was a very efficient and useful way to collect data. This is not a situation, not a database that's based on voluntary submittals. We actually aggressively went to the source to collect the information, and we think from the 121 world, 135 world, that we collected a very good set of data, for our purpose, which was very specific to engine ingestion. The manufacturers also did some cross-checking. The information that they did collect through the field reps, and they did some cross-checking with their airframe customers, just making sure that important events were not missed, because obviously the airframers have their own bird strike information also. And there was also some cross-checking with the FAA wildlife database, again, just looking for some of the major events, making sure that nothing important was missed. So once the data was collected, it was further analyzed by the rulemaking team, and the important outputs of the data effort were very specific bird ingestion rates as a function of bird size and engine size, engine power loss rates as a function of bird size and engine size, and then from those two we can get a feel for what the dual engine power loss rates have been from those. So those three items were the important things that the rulemaking team was able then to use to try and design a rule. But again, the important thing is that again, this database was not based on voluntary submittals. Our needs were different, very specific. So we actively went out, again, to the operators, to the folks who fly the airplanes, to collect whatever data they had, try and fill in the blanks as best as we could on all the different parameters for the event. And we think we do have a good, significant database from which that we drew our conclusions. But having said that, and again, as Bob had mentioned earlier, relative to this accident, it's telling us something. So we're going to go back and we're going to do that all over again. We've already initiated a program to do that, put the team back together to update our database through 2008. We'll also be looking at, and trying to look at what the threat really looks like as far as ingestion rates go, determine whether we can meet our safety objective, or still meet our safety objective. And we're also going to look at some other things, such as our methods of compliance, the type of testing that we're doing, make sure that we're doing good tests and getting out of it what we need to get out of these tests. And we'll probably also talk some engine technology issues, where things have gone since this rule team last did some formal work. So we already have that program in place and are moving forward with that. So, but that's a summary of the kind of the database activity and how the information was used.
Thank you. You talked about a group that meets, and I'd like to know who this group is. Who meets? Do they meet periodically, or do they meet only when an amendment is due? And who comprises this team?
Okay. Well, first of all, we do not maintain a standing study group for our engine bird ingestion rule. That we have not done. What I'm referring to is a formal, the convening of a formal team for a specific purpose. When we did the two rulemaking efforts, Amendment 20 and 24, we had a rulemaking team that was worked through our ARAC process that had representatives from all the major engine manufacturers, the authorities, FAA, JA, EASA, and Transport Canada. We did have representation from some other groups. The last rulemaking we had representation from ALPA. It is open to any organization who wants to participate. But we generally convene that type of a working group when there's a specific task at hand. So we knew we needed to do some rulemaking, so we convened that group to do that job and do it right. But in between those specific efforts, we do not maintain a standing study group to continuously do monitoring. That we have not done.
So, if I can clarify, there's a USDA database that exists. Then there is the data that you actually collect when an amendment is pending. These are the two databases you're working from. And the one that is the amendment type of database is only started periodically. So when the next amendment is due, it looks back in the for the last series of years.
Yes, that's the way we've worked. Our bird ingestion rulemaking database, again, is specific to engines. The FAA wildlife database is not specific to engines. That covers all of aviation. But when we're doing rulemaking, or if we're doing policy and guidance work too, we could possibly do the same thing. But yeah, we would convene a specific working group to actively go and obtain the data that we needed for our specific purpose. And that's what I had explained a few minutes ago, how we do that.
Right.
But in between those efforts, which are significant efforts and take some time to manage and execute, in between those major efforts, we do not maintain any other type of a group or populate any other formal database in between those efforts. Again, the rulemaking or the FAA wildlife database, which was discussed a couple days ago, that's a very extensive piece of work too. And I think from the folks on the airport side, I think that works very well for them. And I think, as Dr. Dolber said, that gives a really good overview of the threat, in North America that we're confronted with. But we're we're just a subset of that, so we actively go and collect the very specific data that we need to do our engine rule work. And what we have collected too is worldwide. All the manufacturers, customers worldwide, are provided us with data. So we think what we did was very appropriate for what our particular task was.
Thank you. The span that you have between the last two amendments, let's say 2000, and now you're starting a new one in 2009, the data that is accumulated at that time, are you satisfied with the validity, or that data is actually accumulated and saved somewhere in the at the manufacturers?
Yes, well, the manufacturers do collect a lot of this data, maybe on a yearly basis. I think for their customers, I think they're continuously asking them for what their experience is with their products. So, and again, that's done through the field reps. So, yeah, we're confident that in between our formal rulemaking activities, that a substantial amount of data, useful data, is collected and will be available, when we need it, when we convene a formal group to do some work.
Thank you. We know that the engines in the Hudson River event were certified to the bird ingestion rules in effect in 1993. Since then, we know that 2 significant amendments have been made to the ingestion rules. So the question is, if a similar sized engine such as the CFM56 were certified to the latest bird ingestion standards, that's number 24, would it be capable of sustaining a strike such as that in the Hudson River event?
Well, I think it's probably impossible to say whether any Amendment 24 product would survive this event. As was mentioned earlier, our regulations don't go there. This was two Canada Goose engine birds into one engine and 1 or 2 into the other. That's beyond the cert requirements for any size engine currently. So it really would be speculation to try and state whether any Amendment 24 engine could survive it. But certainly the Amendment 24 requirements with our new large flocking bird standard, engines will be more tolerant of these larger birds. The Canada Goose, the size also. But again, a lot depends on the parameters of the event. What the power setting is, the wheel speed, the impact location on the front of the engine. There's an awful lot of factors involved and that determine what the result of the event's going to be. But we just couldn't say that other Amendment 24 products would survive this.
Right. Yeah. Maybe that was incorrectly phrased, but certainly the present standard of weights is significantly less than what the event engine experienced.
For the size engine, that's true. The maximum bird size for CFM size is a 6-pounder, and that would be at a safe shutdown requirement. Mm-hmm. But our large flocking bird requirement under Amendment 24 does require a run-on with birds up to 5.5 pounds, for the larger size engines. So, there will definitely be an improvement in overall fleet capability for that reason. And we think too also that with newer engines coming online, they are performing better in a bird environment than older products, and as older products are retired from service, that we believe the overall fleet capability is going to definitely continue to increase and get better. We just hope that the threat doesn't get worse at the same time.
Thanks. And my final question is has to do with the small birds, and also power settings. My first question is why do certification regulations only require bird ingestion tests to be performed at high power settings? And let me continue with the question and to give you the whole intent. On a recent accident, many small birds were ingested into the engines of an aircraft during the landing phase. The engines were at a partial power setting at this time, and both engines stalled and did not recover until the aircraft struck the ground. Should there be certification standards to deal with bird ingestions during a part power condition, such as during landing conditions?
Okay, well, you're correct that our regulations do focus on the high power situation. That's certainly the most critical for fan engines. That's certainly the most critical for fan stages. And those high power conditions are going to occur during takeoff, roll, rotation, initial climb, and multi-engine ingestion of birds under those conditions and multi-engine power losses at that point, could be extremely challenging for flight crews. So we still do consider that those high power conditions to be, extremely important, and we need to maintain our rule focus on that. But as far as the low power issue goes, that's probably more important for the core ingestion situation. I wish we had core ingestions here with the lack of centrifuging at lower power conditions with a shot, or with a bird impact aimed at the core inlet. So that's probably an area where we need to focus on more, and that is actually an area that we're going to talk about or discuss with our database update team when we talk about some technology issues and method of compliance issues. Are we really exercising that situation properly or enough? Because our core shots are conducted at high power right now, the way that we have the tests laid out. So that is something that we do need to discuss internally in the FAA and with industry, in the future. We do need to do that. As far as the event that you talked about, that situation, that accident is still under investigation, and we don't have a lot of information about that just yet. But that appears to be a situation where the airplane flew through a extremely large flock of birds. We don't know how many were ingested into the engine or into the core, but I'm not sure that event right now is going to be a low power versus high power debate. Turbine engine is very sensitive to foreign matter, and whether it's bird mass or hail or ice or volcanic ash or whatever, enough mass going into the core is going to cause operability problems. So we're aware of that event, and we need to understand that better and consider the low power situation also.
Thank you. And that concludes my questions.
Okay, no more questions from the technical panel? Yes, please.
Good morning, gentlemen. Thank you. I just have a couple follow-ups. The first one, in one of the slides, it was shown that a safety objective is to not have dual engine loss due to bird ingestion and something like 1 billion flight hours, the 1 to the 10 to the minus 9th objective. And I was just curious a little bit on how that number is counted. I think I heard something that on like the CFMs we have maybe 500 million, but I'm just curious as to how many hours on the fleet we have already, and whether it includes all engines or just specific types, and kind of where the clock starts in that counting.
That 10 to the minus 9, or the extremely improbable level of safety, that's the objective that we established for the rulemaking, and we tried to design a rule that could meet that objective, that level of safety for a fleet that fully complies with Amendment 24. That basically, so where the time starts and stops, I guess officially it would start with the adoption of Amendment 24 and include Amendment 24 engines into the future. But obviously that's not the way the industry works. All the products are there and they continue to operate. So, but again, that safety objective was established for Amendment 24 with the intent that a world fleet that met Amendment 24 should be able to operate at that level of safety. Now, to put a perspective on kind of where it seems to be today, since the start of service of the large turbine aircraft in the 60s, air carrier type aircraft, we have over 550 million flights since then, and over 1 billion hours since then. These are air carrier hours and flights. And in that time period, right now we have two forced landing hull losses due to multi-engine power loss due to bird ingestion U.S. Air being one. Previous accident occurred in 1988, was a two-engine transport. It was an accident in Africa. There was a multi-engine ingestion of rock doves and multi-engine power loss and an accident there. So those are the two. Those are the two events that we're recording right now that our safety objective was specifically targeted for. It's the multi-engine ingestion, multi-engine power loss situation, and that's where we're trying to provide this extremely improbable level of protection for. This third event that we just discussed a minute ago with the smaller birds, again, that was also a multi-engine power loss situation. That's still under investigation. We need to understand that. So we're not characterizing that one way or the other at this point. But that puts a perspective on kind of where we think we are.
Okay, thank you. And just to make sure I understand you then, and I think we have over 1 billion hours, but 2, maybe 3 events. Is that correct?
2 or 3 events of multi-engine ingestion, multi-engine power loss, where sufficient thrust was not available for safe flight and landing. That's correct.
Thank you. This next question might be kind of silly, but I'll ask it anyway. And I understand that the U.S. Air event, because of the bird masses, is way outside the CERT criteria. But the question regards the safe shutdown criteria and the preclusion of disk rupture or catastrophic failures or fires. And Mr. Campbell, in his testimony on Tuesday, characterized one of the engines as being a bonfire, and understanding that we're outside the CERT criteria. But I'm just wondering if that description would be precluded for a safe shutdown within the criteria.
If you look at the 2 engines, one was safely shut down. That was the number 2, the right-hand engine. And Mr. Campbell was speaking about the left-hand engine, number 1, which continued to run. And from what we can tell from the data and what we see from the engine, the large bird requirement says not catch fire. That is an external fire, really, not what we saw in this engine. What happened on this engine was the core was severely damaged and had little airflow flowing through it. So although it could keep the core rotating at something like 80% speed, the fan just didn't have enough airflow through that core because of the damage to power the fan. So what you ended up with was it was feeding it fuel, and the fuel was coming out of the back, out of the nozzle, the core nozzle. And once it got to the oxygen on the outside, it could burn there. So you were seeing a fire out of the nozzle, which was just unburned fuel. It didn't catch fire, as would be defined for the large bird requirement.
Okay, again, so to be clear then, so while that site may have been spectacular, from a safety point of view, it wasn't really a danger, as risky a fire as the sort of fires you're contemplating in the CERT rules. Is that a fair statement?
That's correct, yes.
Okay, thank you. And lastly, I was wondering if you can help me understand why the the single large bird requirements masses are dependent on engine size. Is there a statistical connection between the size of the bird and the likelihood that it's going to go into an engine of particular size?
That is correct. For all the bird sizes, there is a strong, the data that we collected, the database that we have, the bird ingestion rates that we've observed, as a function of bird size and engine size, is a clear difference between the sizes and numbers that are typically ingested. Large engines have a strong tendency of ingesting larger birds, this accident aside. They also have a tendency to ingest many more of them. As far as the large flocking birds go, those greater than 2.5, large engines will have single ingestion rates 2 to 3 times higher than the smaller engines. For multi-engine ingestion rate, it'll be 10 times as higher. And the size of the single large bird, it really is the same thing. That the larger engines will have a tendency of taking larger birds, and also to maintain an equivalent level of safety, they need to be challenged harder for that reason.
Okay, and by going into the engine, we're talking anywhere in the fan area, not just the pink area that Mr. Ganley showed. Is that correct?
The single large bird test, the target needs to be the critical location, and that means that's the feature on the engine that's least likely to survive and pass the test. So there's going to be an analysis done ahead of time to determine what the critical feature is for a particular engine. Could be the core, it could be a fan feature, but that does need to be determined before the test is conducted.
Okay, and I'm sorry for not understanding completely, but when the statistical correlation that you mentioned between the large engines and the large birds, is that referring to the birds that go into the core because of the, I presume then the larger engine, that core size will be, that pink area will be larger? Or is the statistic applied to large birds going anywhere anywhere through the fan?
The statistical correlation is the inlet area, the larger inlet area. So the very large engines have different ingestion rates than the smaller engines do. So it is the inlet area, not the core inlet area that drives the bird size for the large single test.
Okay, and I understand that that's what the statistics show, and it's interesting. Can you do you have any idea from a physical sense why that might be? Why the larger engines might attract larger birds or whatever?
May have just a lot to do with the size of the target. I guess I'd go beyond that, would be maybe speculating. But I do know from the FAA's wildlife database, where they have some information in there about the different features on an airplane and how they're struck. In general, strikes seem to take place relative to the area of the feature that you're considering. So I guess we do believe that it has a lot to do with just the size of the target.
Okay, thank you. That's all I have.
Thank you. Any other questions from the technical panel? Okay, we've been in here about an hour and a half. Let's take a break. Let's take about a 12-minute break and be back at 9:40. Thank you. Okay, if everybody please take your seats, we'll get restarted.
I wish I had the light like that. Push one.
Okay, thank you. We'll start back with the questioning from the parties, and FAA and CFM International both have witnesses. So, Mr. Harris, you would like to go in which order?
We have no preference, sir.
Okay, very well. And Mr. Mills.
Mr. Chairman, CFM would appreciate going last.
Great. We'll just keep it in order because I believe we're starting with USAPA, so we'll just keep it in order of the table. So USAPA.
Thank you, Mr. Chairman. Good morning, gentlemen. I'd like to start, if I can, with Mr. McVey, a couple of operational questions, if you don't mind. Regarding the fire that was described by the passenger witness, you gave us, I think, a very good technical answer for how or why. But is it safe to characterize that fire as something similar to tailpipe torching on an engine start?
Yes, it would be.
Okay, thank you. And obviously a very innocuous type of event.
In flight especially, because the flames nowhere near anywhere can cause danger.
Thank you. Okay, and Mr. McVey, you are familiar with the flight data from Flight 1549, I assume?
Reasonably, yes.
Okay. Based on that, let me ask you, in the situation of Flight 1549, are there any other flight crew procedures that would be applicable that might gain the crew thrust from the engine other than attempting the restart or the relight?
I can't think of anything else. They saw the engine was running. They attempted the restart, which could possibly clear any stall. Beyond that, there's nothing else they could have done.
Okay, thank you. And had the engines been capable, without the obvious damage that they suffered, did you see anything in the data that would have limited those engines from starting at that point or restarting?
No, other than they weren't really in the restart envelope, but when they did that restart on the number one, it came down, it came straight back up, admittedly at lower thrust level because of the damage, but no, there was nothing preventing them starting.
Okay, and are you familiar with the relight envelope that is provided in both the Airbus and the U.S. Airways procedure and QRH and so forth?
A little, but I don't know the details.
Would it be appropriate, would you mind referring to that? At this point it is an exhibit. I understand you're not responsible for that exhibit.
Yeah, if they can find it.
Okay, could I have exhibit 2AA, please?
Now, Mr. Sicchio, is this witness, it's not tagged to this panel, is it?
That's correct.
Mr. McVey, you may answer the question if you know the answer, but you're not required to because it's not specific to your exhibit, to your panel.
Okay.
Yes, Mr. McVey, if you don't mind, would you, and I understand this is quite small here, but the top chart is the relight envelope for the CFM engines on the Airbus QRH, I believe. Looking at the quick relight envelope, does it appear to you that between sea level and 3,000 feet that it is in the range of 190 knots? Is that fairly
correct,
accurate? Yeah. Okay. And is it your understanding that the aircraft was operating just above that speed for most of the duration of the flight?
I know the ingestion were at 220 on the descent, and I know they slowed down. I'm not sure where they were when they did that relight attempt. They might have been around 190, but I don't know.
Okay, thank you. That's great. Thank you very much. And I appreciate you attempting with that piece of evidence that was not your responsibility. Thank you. Okay, moving on to the certification side. Mr. McVey, you did mention that you had been involved in the ARAC rulemaking process. Is that correct?
Yes.
And were you involved at the working group portion of that process?
Yes, that was for the latest amendment. We met in 2002.
Okay.
Mr. Bouthillier was the chair.
Oh, great. Thank you. And we will also ask you on this subject as well shortly, sir. During that process, it seems from all of the testimony on this panel that the working group seemed to have great results. Did you folks find good levels of cooperation, and was the work done in a timely process?
I thought we cooperated very well, and we did that in, I'd say, 2 years. I think it was about 25 months.
Okay, very good. Okay, thank you. Now, Mr. Bouthillier, was that your experience also?
Are you talking the Amendment 24 rulemaking activity?
Yes, the group that you were on with Mr. McVey.
Right. I believe the tasking was done under the FAA ARAC process. I believe the tasking was in 2000, and I believe the ARAC rulemaking team completed its work and delivered its product to the FAA maybe around the end of 2002, and that was very, very efficient in my experience, working rulemaking projects. So we were happy with the cooperation of all the members, and we thought, we were very efficient about it.
Okay, thank you. Yes, it sounds as if you had a very good team and worked well together. That being said, could you describe the process once it leaves the working group? What happens to the rulemaking at that point? Yes, I'm sorry, Mr. Bouthillier.
Once the recommendation the work is complete within the ARAC working group, they deliver a recommendation to the FAA. At that point, it's up to the FAA to process the rule. So the folks that worked on that ARAC rulemaking team are now not actively engaged in the processing of the rule.
Okay, and could you tell me how long that process from the time it left the working group until final rulemaking? Could you give me it
was approximately 5 years.
5 years. So it's correct to say then that the working group accomplished their work in approximately 2 years, but it took the FAA yet another 5 years to actually publish the rule?
That's correct.
Okay, thank you. And thank you. That's no further questions.
Thank you, Captain Sicchio, AFA.
Mr. Chairman, AFA has no questions.
Thank you, Ms. Colander. FAA.
Thank you, Mr. Chairman. We have a few number of questions, actually. Mr. Ganley, you were present, I believe, yesterday when Mr. Brenneman testified to the FAA certification of the aircraft relative to the bilateral agreement.
Yes.
And in that discussion was the recognition that FAA, for example, could have independently declined or disapproved the application for the aircraft, even if DGAC chose to approve it. In this joint certification process, particular to the CFM products, is that the same relationship? Can one authority certificate without the other authority agreeing to?
I'm not sure I can answer that 100%. I can say in my experience that it's never occurred. Each authority is responsible for their own regulations, and to my knowledge, every certification has been done jointly.
Right, and so in fact, in history, they've jointly issued in that respect, correct?
That is my understanding, yes.
Thank you. Again, to Mr. Ganley, Mr. Bouthillier spoke of the potential of up to 2 to possibly 3 multi-engine power losses related to bird ingestion resulting in hull losses of aircraft. Of course, as we recognize, U.S. Air 1549 is one of those. In roughly the 1 billion flight hours flown since the 1960s. You remember that testimony?
Yes, I do.
And also the discussion was that the target level of safety of Amendment 24 was 1 in 1 billion flight hours, or roughly 10 to the minus 9th.
That is correct.
But in fact, is it not true that if we were to look at those flight hours accumulated from the 1960s over the 5 decades of those flight hours accumulating. The vast majority were not involving aircraft certificated under Amendment 24, the 2007 amendment. Is that correct?
That is correct.
And even a substantial number of those were not under the Amendment 11 under the 2000 amendment. Would that be correct?
I believe that would be true also.
And there's even a fair number of aircraft engines that were certificated prior to Amendment 6, which was the 1970 amendment. Would that be correct also? Worldwide. And fair is a rough number. So are they present in the fleet? And certainly in those hours accumulated?
Yes, I think when you look back at 4 close to 5 decades of worldwide fleet experience, I think it is safe to assume that many engines are very old in that time frame from the 1960s forward. So I think that's a fair assessment as well.
Okay, thank you. So that more or less puts that in perspective in terms of the numbers of events over the years relative to Amendment 24. Maybe you can comment on that. I
think that is indeed the case. The vast majority of the service experiences I just noted are on pre-Amendment 24 engines. And even though that is the case, I think that the field experience is quite well. And I guess I'll leave it at that. Thank you.
Thank you very much, sir. And Mr. McVey, just one minor question. It was earlier discussed from the USAPA folks that the quote bonfire, as Mr. Campbell referred to it, was similar to tailpipe torching. Is this the kind of fire in the exhaust stream like that? Is this the kind of fire that typically triggers an airframe fire warning system in the cockpit?
No, it doesn't.
Okay, thank you very much. We have no other questions, sir.
Thank you, Mr. Harris. Airbus?
No questions, Mr. Chairman.
Thank you, Captain Canto. U.S. Airways?
No questions, Mr. Chairman.
Thank you, Captain Morrell. CFM International?
We have no questions, but I'd just like to say how thorough I think the panel has been in answering the questions. Thank you, Mr. Chairman.
Thank you. Any follow-up questions at all from the parties?
None from USAPA, Mr. Chairman. Thank you.
Thank you. Seeing none, any follow-up from the technical panel? Great. Board of Inquiry, we go to Dr. Colley.
Yes, Mr. Ganley, can you answer why is a 4 to 6 pound bird chosen as the mass for the large bird? When we saw testimony yesterday from Dr. Dolbear about the numbers of birds and the sizes, their masses, which there are a significant amount much larger than that.
To be honest, I think not being part of the actual ARAC rulemaking process, that Mr. Bouthillier would be better suited to answer that question. But it is my understanding that the rulemaking team did consider birds much larger than where the standards ended. But the specifics, how they came to 4, 6, or 8 pound birds, I'm not that sure, to be honest.
Is the question relative to the large single bird requirement?
Yes.
Yeah, the data that was collected and evaluated, indicated to us that with the size engines that those 3 size birds would be applicable to, that those are substantially the worst case single large bird or single engine event sizes that we had experienced, and that primarily is how that was selected. Birds greater than 8 pounds. I don't think showed up in the data that we had, even for the large engines. That was a while ago. But anyway, they were selected based on actual observations of what had actually happened in service.
And so how does this incident affect your thinking in that?
Well, this accident and this level of ingestion to this size of engine is I guess unprecedented in our data. And as we go back and update our database, we need to take a good hard look at what happened here and reevaluate that, no question. But again, we will be looking at all the various ingestion rates and the engine power loss rates, and taking a step back and reevaluating what we did, back in the 2000 time period. No question we need to do that.
Okay, thank you. Mr. McVey, I have a couple of questions for you. I wonder if we could pull up slide 11 from your presentation. Could you explain to me what is the threat posed by bird ingestion to a modern turbofan engine? There's been a lot of discussion about if a bird is ingested into the booster inlet versus the bypass duct. Can you tell me what types of damages occur in those scenarios?
In the majority of ingestions, I mean, as I said earlier, all birds go in the front and they hit the fan blades at some stage. Typically the booster inlet, anything headed towards the booster, you're talking maybe 10% of the time you might get something in the booster. The fan blade is the most critical part in most ingestions, and every bird hits it, so you have to look at maintaining the integrity of that blade. We see typically 80% of the time no effects at all. Beyond that, when the birds get heavier, you'll see damage to the fan blades. We get distortion, you get dents, tip curls, stuff like that. You might also get other minor damage to the OGVs, which are in the bypass duct, and the outer panels, just from the impact of the bird being slung out there. Once the bird enters the core, depending on the mass that's entered into that core, that's when you get the more consequential damage that we saw in this event, in this accident, when we got a large amount of meat into the core, and it severely damaged the booster and then consequently damaged the HPC downstream.
And it's the damage to the core that primarily prevents the relight, the ability to relight the engine?
Typically, if you get a severe core ingestion, it would be, yes, but you can get cases where you got severe fan blade damage where the engine cannot run on.
You talked about the possibility of any future designs, and that might be, I guess, that might be able to take bird strikes better, let's say. And you said that it didn't appear that there was anything that you could identify immediately. I wonder, in the area of advanced materials, I know that your engine groups are constantly looking at new modern materials. Is there any promise in the future that you're aware of in using these advanced materials that may toughen the engine up and maybe mitigate the effects of a bird strike?
If you look at the more recent engines, the larger engines, we're moving to composites on the fan blades, and they've been a step change in capability on the fan blades. They've improved, but that technology can't be extended down to the small sizes of core blades. Also, they won't take the temperatures in the back end of the compressor, so it gets very difficult with materials. The technology at the moment to take a huge, something the size of a goose into the core is beyond current technology, really.
Okay, thank you. And I have one clarification. Mr. Ganley, we were talking about new engines being affected by new rules. Do you mean newly manufactured or new engine designs would be the types of engines that are affected by any new rulemaking?
It would basically be any new engine for which an applicant submitted an application for a new type certificate. So, for instance, if CFM International came forward with a CFM 56-8 and it was a derivative engine model of a current -5, that would not be susceptible to the latest regulations. So it would be a new engine model that came forward. As part of our process, I mean, there is something, our 21-101 requirement, even for amended type certificates, requires that people look at the latest amendment, and they need to determine whether or not we should be looking at the latest regulations as we move forward on our certification programs. But in general, something like bird ingestion probably, with the types of changes that we see in these amended models, would not rise to that level. So again, new engine.
Okay, thank you. I have no further questions.
Thank you, Dr. Colley. And Mr. DeLisi.
Thank you. Mr. Bouthillier, perhaps you could help clarify something that is confusing to me, and it seems to be a bit of a dichotomy in the certification standards. You were talking about the standard, the new standard for large flocking birds, and I think you described that the requirement is to ingest one of those birds. Is that correct?
That is correct. The Amendment 24 revision that included the new test for what we're calling large flocking birds is for a single bird ingestion.
Right. So if we're identifying that those birds are flocking, why would the standard imply that you'd only take one?
Well, the standard is implying that more than one engine on an aircraft is affected during the same encounter. So that one large flocking bird and one engine, the assumption is that there'll be another one in another engine. So it's not it's a flocking. It's there to represent the flocking situation relative to the airplane, not necessarily a flocking situation relative to any individual engine. So again, there's run-on requirement for that new standard, and that's under the assumption that there are going to be multiple engines on the airplane affected.
Well, thank you. And then the other half of that dichotomy to me is the large single bird test standards. We heard testimony from Dr. Dolbeer that large birds fly in flocks, dozens, hundreds, thousands. Certainly this event identified large birds flying in flocks, yet that standard is defined as a large single bird. Why don't we acknowledge the flocking nature there?
Well, the key is to look at the difference between the flocking standards and the single large bird and relative to the size of the engine that you might be interested in. The flocking bird standards will be smaller for a given engine. The flocking bird standards are smaller than the single large bird. And that gets back to the nature of or what our data is telling us of the types of birds, the sizes of birds that typical engine sizes generally ingest and the rates they do so. So a smaller engine that may only be required to ingest 1.5 pound birds, it's going to have a 4 pound single large bird standard, which is quite a bit larger. So you have to look at the two together. But we do understand that there are birds much greater in size than Canada geese, and they do flock. But again, we'll get back to the data and our safety objective and trying to develop something that provides for a high level of safety, but also standards that can be met.
Thank you. And I'd like to just get the panel's general thought on this idea. Certainly the testimony from this morning makes it clear that an encounter with a large bird greater than 4, 6, 8 pounds, we don't expect a turbine engine to be able to continue to operate. So it would seem to me that an important takeaway from the Flight 1549 accident would be that we really need to stress the technology and the procedures to avoid encounters with flocks of large birds. And I wonder if you'd care to react to that.
I think as I'd shown earlier in one of the slides, it's obviously a very complex issue. I don't think any single element can address the threat. So I agree that I think that a concerted joint effort in trying to look at all aspects is needed to mitigate the threat. So I do agree.
Great. Please.
Just one other comment, too. Relative to the cert requirements, again, we've established them for as a function of engine size, but and I think as we've seen in the accident engines here, that the engines don't fall off the cliff when you go just a small amount above what the certification standard is. There's a lot of margin built in overall to the cert process, to the engine design process, and even with the larger birds, the 8 pound birds that you mentioned, certainly with our large flocking bird standards, even those that are required, the largest bird there was 5.5 pounds. That's an average snow goose. That's another threat species. There will be capability beyond what the search standards do require. That was part of our evaluation. We understood that, in designing the rule, and the expectation is that there will be. But again, it gets down to the parameters around a given an ingestion, the target location, the wheel speed, power setting, other factors. So, but we do believe that the capability is going to continue to improve, into the future.
Thank you. Yes, Mr. McVey.
One other comment, just backing that up. I mean, we do see ingestions in service with large birds, 468, and there is sometimes no effect on the engine. It's totally dependent on the ingestion condition. So it's not that there's no capability with a 46 or 8, but it just depends how it's ingested.
Thank you. And Mr. Bouthillier, you reminded me of something I had jotted down when Mr. Ganley was speaking. You talked about how there isn't really a cliff, and I think you were mentioning at a 4-pound standard, if a bird was 4.1 pounds, we might very well have an engine that could withstand that. You used the word withstand. Just wanted to be sure that we're clarified. By withstand, you don't mean continue to run and operate.
Well, what I know is to still comply with whatever the standard was that was in question. So for safe shutdown, the CFM, for example, that its cert basis was 4 pounds. Under the current amendment, it would be 6. But here, at least one of these engines ingested 2 Canada geese at high power setting in 2 different locations on the fan, and performed quite well relative to the safe shutdown standard. So this is a good example of where the engines that we certify and are being produced don't fall off the cliff.
Great. Thank you.
Thank you, Mr. DeLisi. Mr. Bouthier, you had mentioned that multi-ingestion power loss accidents, and I believe you, of course, referenced the U.S. Air 1549 accident and one in Africa, which might have been Ethiopian Airlines.
That is the Ethiopian event, yes.
Yeah, and that was in
1988.
Okay. How about and were you just referring to civilian airplanes?
Yes, just civilian airplanes and Western aircraft that we have responsibility for and information about.
Any other accidents in perhaps military fleets involving a CFM 56 engine that you can recall?
There was a major accident, Elmendorf, back in the 90s. I wasn't aware it was a CFM-powered airplane, but yeah, that was a large transport-type aircraft.
Okay.
Those are snow geese, I believe. They had a problem with.
Yes, okay. 24 fatalities out of that one, I believe. I forget the year.
Probably was around 96 or 98 in that time period.
Thank you. But the point is that that was a bird ingestion transport category airplane. In fact, that airplane, the EC-135, would be the same as a Boeing 707, which is not in use anymore, but nevertheless it is a transport category airplane, I would assume. Is that correct?
Yeah, they're large transport category aircraft.
Right. Thank you. Yeah, large transport category. Thank you. Mr. Ganley, the bird population, as we've heard, we've received testimony that the bird population is increasing, and we talk about the historical perspective of how these engines do. There have only been 2 accidents involving commercial transports in the last 21 years or so, but is using a historical perspective reasonable when we had a dual engine flame out in November of last year with Ryanair, and then 2 months later we had the U.S. Airways accident. So when we talk about a historical perspective, is that realistic when figuring our risk assessments, probability, things like that?
I mean, certainly the 2 events that you're noting there have given us pause that we need to go back and reevaluate the overall level of safety of the fleet, our safety objective. So, I think we need to gather that data and analyze it and see what changes, if any, need to occur. I mean, statistically speaking, it's pretty incredible that those, 2 events happened, in the timing that they did. but that's something we need to go back and evaluate. I don't think it would have been forecast. In fact, it's my understanding, even when the rule team did their work, they tried forecasting 10 years into the future, which would have put us out into about 2010. And I'm not sure they would have anticipated these two events occurring, at the timing that they did.
Thank you, and I think it lends even more weight to what Mr. DeLisi posed just a few minutes ago, that it does, and you agreed to that it needs to be not a single bullet, but a comprehensive system-wide approach to addressing this issue. And so it's an easy question to ask, but I'm sure a very difficult one to answer. Are the current certification standards, are they adequate? Are they sufficient? And
we do think they are. We've had two recent rulemakings in 2000, 2007. Those are based on bird threat studies that were conducted through the 90s to year 2000. And we attempted to address that changing threat with a very conservative safety objective for the rule. And as part of that, what we also did, we did predict out 10 years what we thought the bird ingestion rates would be, given the continuous increase in populations we're seeing, especially on the larger flocking birds. So we made an attempt to try and, even though our data was through 2000, we made an attempt to try and get to 2010 at least with the bird ingestion rates. And the bird ingestion rate was a very, very important parameter in the rule design, how often things happen. So we did make an attempt to do that. Also, too, with newer products coming online, and the fact that a lot of engines that were certificated even in the mid-90s were anticipating the rule changes. So those engines were being designed with more in mind. So we think newer products are going to continue to perform even better in service. But again, like Bob just said, that we've got some data points here that we need to deal with and understand.
Thank you. Mr. Ganley, your comments, are the current certification standards, are they adequate?
Yeah, I think until such time as we analyze and see if there is a need, I guess I would say they are, satisfactory today until shown otherwise.
Thank you. And Mr. McVey, same question.
Yeah, I have to agree. I think, when you look at the data, we need to review it, but I think we're meeting the intent of the regulations at the moment.
I had briefings from members of the head of FAA certification a few weeks ago on engine certification standards, and basically I walked out of that meeting, or they walked out of that meeting with my thinking that really we can't do a whole lot more with engines. We might be able to beef them up just a little bit more, but we can't design and build aircraft engines that can fly on airplanes that can withstand a 20-pound bird or something like that. I suspect that's true, but I also believe that until you identify a need that something needs to be changed, you won't achieve it. I look at, for example, crash survivability issues in automobiles. We've done a lot in that area over the years. Fuel economy in automobiles, we've done a lot over the years. A few years ago, a car would get 16, 15 miles to a gallon. Now they're around 25 miles to a gallon, and the President has just announced a CAFE standards that says that the manufacturers have to come up with automobiles that have 35-mile-an-hour standards. So, we can keep moving that bar, and so I just throw that out there that maybe we can if we raise the bar, and that will be perhaps something that the board will look at, is are the current certification standards adequate, and can they be reasonably raised, and that might be something that we would look at. Mr. Ganley, I want to ask you, these high bypass turbofan engines are remarkable. They are very fuel efficient compared to their predecessors. They are much quieter than their predecessors, but I started flying with a JT8D engine, which was probably about this wide, and it had inlet guide vanes, fixed inlet guide vanes at the very front of the engine. Now we look at these CFM engines, which I could stand up in, and the very front of the engine is the actual fan part, and that's the part that's moving, so there's nothing to deflect objects other than the centrifugal force of something actually hit it. Are we more susceptible to bird strikes with these engine bird strikes with these larger engines? I mean, you would stand to reason that since the circumference of them is the diameter of them is much larger, you would think would be that in itself would create issues. So tell me about that.
I think, as Mr. Bouthillier had mentioned earlier, is certainly the function of birds hitting the engine. It's a function of the frontal area or the exposed area the birds come in. So when you talk a CFM engine that's roughly about a 5-foot diameter, or some of the largest engines out there, 10-foot diameter, you would expect many more bird strikes on a huge 10-foot diameter engine. Getting to your comment on, inlet guide vanes, certainly anything upstream of the fan blades that are rotating that could conceivably minimize the impact of a bird coming in is a benefit. But as you said, there's trade-off imbalances of weight, efficiency, SFC, emissions, and other things. So all those things need to be taken into account. And again, I think it just gets back into, the exposed frontal area for which the birds are being projected to.
Thank you. Thank you very much. We're about to wrap it up, and as we do, I really want to thank the parties for your excellent questions and for your cooperation. Captain Sicchio, I'd like to thank you and your colleagues at USAPA. Ms. Colander, you and the FAA, or Association of Flight Attendants, thank you very much. Now we address the FAA. Mr. Harris, as usual, thank you. Airbus, Captain Canto, thank you very much for your participation. Captain Morrell, U.S. Airways, thank you. And CFM International, Mr. Mills, thank you and your team for being here. So with the last witness having been heard, this concludes this phase of the Safety Board's investigation. In closing, I want to emphasize that this investigation will remain open to receive at any time new and pertinent information concerning the issues presented. And the board may, at its discretion, again reopen the hearing in order that such information may be part of the public record. The record of the investigation, including the transcript of the hearing and all exhibits entered into the record, will become part of the Safety Board's public docket on this accident and will be available from the Safety Board's Public Inquiries Office or the website. Anyone wanting to purchase the transcript, including the parties to the investigation, may contact the court reporter directly. So there's the inevitable question, is when will this investigation be completed? Well, there's still a lot of work to be done, a lot more work to be done before the staff will be able to present a report to the board. Again, we're still in the fact-finding stage at this point, and this hearing is a very important part of that fact-finding process. But I assure you that we will conclude the investigation as soon as possible. So I do want to thank again all of the parties for their cooperation, not only during the proceeding, not only during this hearing, but throughout the entire investigation. I want to express my sincere appreciation to all of those groups, persons, corporations, and agencies who have provided their talent so willingly during this hearing. Thank the audience and the media for being here to show your interest and to help get the word out as to what's being done to improve safety in this country. There are a lot of people who work behind the scenes to make these things happen, and people that never get seen or recognized. Rochelle, Eunice, Fernando. Up in the audio booth providing tech support and audio, we've got Greg and Brian and Antoine. We walk by these security guards every day. We probably wonder why we have to put our keys and our BlackBerry on the belt and all, and then when we learn of the tragedies such as occurred yesterday, just a few blocks from here, it all sort of brings it back home. Those people are here to protect us, and I appreciate what they do. And finally, I want to thank my special assistant, Heather, who will leave this job next week for a much more important job, to go take care of her child. And I appreciate very much the fact that she was willing to stay on for an extra couple of weeks to help me get through this hearing. I now declare this hearing to be in recess indefinitely. Thank you very much.